Now we're going to discuss truth tables. A truth table is a way where we represent all possibilities of a statement either being true or false. Now for any statement P or Q, we've discussed ways to make new statements out of them like negation, conjunction, disjunction, and conditional statements, so we're going to give truth tables for those things. Here's a truth table for a negation. Okay? If you have a statement P, then there are two possible values for whether that statement is true or false. We account for those with these two rows. The statement not P, however, depends entirely on P. In the row where P is true, not P is false, and in the row where P is false, not P is true. Let's move on to take a look at conjunction P and Q. We understand conjunction to mean P is true and also Q is true. Well, there are two underlying statements, either of which could be true or false, so overall I need 4 rows to account for the various possible combinations. Maybe they're both true, maybe P is true and Q is false, maybe P is false and Q is true, or maybe they're both false. Now in each row I ask the question, what about P and Q? Is it the case, yes or no, that P is true and also Q is true? Yes, in the top row P is true and also Q is true, so I call this true. In the second row, P is true, but Q is false. So was it the case that both were true? No, I call this false. Note that I cannot call it something like half true, because a statement must be either true or false, but not both. And that is a combination of the law of the excluded middle and the law of contradiction. So I have to call this either true or false. And I'm interpreting conjunction as both being true. So if either one of them is false, overall the conjunction is false. And certainly if they are both false, the conjunction is false. Now let's take a look at disjunction. Here we're building up the statement, is it the case, yes or no, that either P is true or Q is true? Well, I'm built out of statements P and Q, so I have the same 4 possible combinations of their truth values. If either one of them is true, I say that the disjunction is true. This is not an exclusive OR, so if they're both true, then the OR statement is true. The only scenario in which the disjunction is false is when both of its components are false. Compare this to conjunction. The only way a conjunction is ever true is if both of its components are true, otherwise it's false. The only way a disjunction is false is when both of its components are false, and otherwise it's true. Now, as interpretations of and versus or, these are pretty uncontroversial. Students get an intuitive grasp of this quite quickly. But let's talk about conditional statements where intuition can fail a bit. Now, P implies Q has the same 4 fundamental rows that I need to figure out because it has the same underlying statements P and Q. The thing to be clear about is that implication is not any sort of causation. P is any statement I want and Q is any statement I want. And I am not saying somehow that one statement causes a change in the other. They exist on their own as statements. This logical implication arrow is not some sort of causality or changing. All I'm doing is forming a new statement and deciding, do I want this new statement to be true or false? Well, if the hypothesis is true and the conclusion is true, I ask myself, do I want to say a true thing implies a true thing? Sure, let's call that true. Does a true thing imply a false thing? Is a true hypothesis going to lead to a false conclusion? No, I want that to be false. And these 2 rows are pretty quickly understood and intuitive. Where students can go wrong, however, is in the last 2 rows. These 2 rows account for the scenario where what if the hypothesis P is false? Does a falsehood imply something else? Yes. Okay, we call these 2 things vacuously true, but when the hypothesis is false, a conditional statement is said to be vacuously true, but that does mean that it is true. Okay? Many students object and say, I don't want a false thing to imply anything, so I would like a false hypothesis to lead to a false conditional statement. However, this leads to the following problem. If I were to use this truth table for a conditional statement, it would be exactly the same as a conjunction. And logical implication shouldn't be the same thing as and. So I don't want to make both of these false. Now there are reasons why I don't want to make one of them true and one of them false that I don't really want to get into here. At the worst, just understand that by definition, we are saying a conditional statement is vacuously true in the scenario where its hypothesis is false. Now we can use these truth tables to construct new truth tables for larger and larger compound statements by following these instructions. First, you look for all the literals in your statement. Whatever statement you're trying to construct, it's going to have one or more literals or just individual letters that are used to build it up. The rows of your truth table must account for all possible combinations of truth and false that could happen to those literals. Each different combination needs its own row, and you need a row for every possible combination. You start your table at the left side by declaring your literals and listing out all possible true versus false combinations that there can be. As you move from left to right, you can do a single thing, a conjunction, a negation, a disjunction, a conditional statement that are built up using statements that already exist to the left. So you move from left to right, only doing a single operation at a time. When you have finally constructed the statement you were interested in, you have finished listing out your columns, and you can then fill in all the truth versus falsehoods according to the rules one step at a time. Let's take a look, of course, at examples. I'd like to construct a truth table for the following statement. P or Q implies not Q. So first we draw a big old table, and it's got far more space than we actually need, right? Well, what are the literals that go into this statement? There's a P and there's a Q and there's a not Q, but as far as letters, it's just P and Q. So I'm going to go ahead and declare I need the literals P and I need Q, and there's two of them, so there's going to be 4 possibilities for the various truth versus falsehood. Okay, those are all the rows that I need. I can, if I really want to, duplicate rows, but this is totally unnecessary because that's going to do the same thing as the first row. Okay. The very fundamental error that I see earliest in this course and that tells me a student has kind of missed the mark is if the number of rows in their truth table is incorrect. If you have a single literal, there are 2 possibilities, true and false. If I have 2 literals, P and Q for example, since either one of them could be either true or false, I need 2 times 2 equals 4 rows to account for that. If there were 3 literals, P, Q, and R, I would have 8 possibilities. True versus false for each of P, Q, and R, 2 times 2 times 2 equals 8 possible rows. The number of rows, other than the top row where you're listing out your statements, is going to be a power of 2. So now what I do is I move from left to right, building up by one operation at a time until I can build the statement that I'm interested in. So for example, in order to ultimately end up at the statement P or Q implies not Q, before I can do that, I need to build its hypothesis, P or Q, which I can do immediately because if I put this as my third column, the 2 component pieces, P and Q, already exist to the left. I can also negate Q because Q exists to the left of that column, so that will be permitted. And now, since I have P or Q, I apologize, and I also have not Q, I'll be able to form the conditional statement P or Q implies not Q. Now I need to construct the truth table going column by column. So in the third column I ask, in each row is either P or Q true? Yes, they both are. Yes, P is true. Yes, Q is true. No, they are both false. Now I ask in every row, let's take whatever happened to Q and negate it. So instead of Q being true in the top row, not Q is going to be false. Instead of Q being false, not Q is true. If Q is true, then not Q is false. If Q is false, then not Q is true. All we've done here is exactly flip what was happening to Q. Now I form a conditional statement. Now remember, a conditional statement is true anytime the hypothesis is false. So I can ask, what's the hypothesis? It's P or Q. Any row where the hypothesis is false, this statement will be vacuously true. And that happens to be the case in the last row. The hypothesis, P or Q, is false, therefore the conditional statement is vacuously true. If I have a true hypothesis and a false conclusion, we wanted the conditional statement to be false in this scenario. If I have a true hypothesis and a true conclusion, well then, we want the conditional statement to be true in this scenario. And row 3, notice, is actually the same as row 1 in that it has a true hypothesis and a false conclusion. True hypothesis, false conclusion means false conditional statement. And now we have completed a truth table for the statement we were interested in. We declared all of the literals and listed out all of their possibilities. Once we did that, we did one operation at a time. I can disjoin P and Q to form the statement P or Q. I can negate Q. Then I can use this as a hypothesis and this as a conclusion to form this conditional statement. And once we've filled all of this in, we're done. And here it is presented just with the 4 rows that we need. Notice this is slightly different than the one we drew on the previous slide. Let's just look that everything is legitimate, however. I declare my literals, and I have 4 different possible combinations. Now I move from left to right asking, can I build the next statement using only things to the left? Can I build the negation of Q? Yes, because I have Q. And all I do is reverse everything that Q had. Can I build the disjunction P or Q? Yes, because P, Q individually already exist. P or Q? Yes. P, yes, so the or is true. If Q is true, the or is true. If both are false, the or is false. Now I can build this conditional statement by asking, hypothesis implies conclusion. But now notice the hypothesis is actually to the right as far as how the table is oriented. That's fine. Hypothesis, true. Conclusion, false. Conditional statement, false. Hypothesis, true. Conditional statement, true. Conditional statement, true. Hypothesis, true. Conclusion, false. Conditional statement, false. Hypothesis, false. Vacuously true. Remember, whenever the hypothesis of a conditional statement is false, the conditional statement is declared to be true. And now let's work through another example. We're going to construct a truth table for the following statement: the negation of P or R and Q implies not P. So how do we begin? The first thing we do is we ask, in the statement we're trying to build, how many literals are there? Well, there's P, there's R, there's Q. Not P is ultimately dependent on P. So I need to make sure that my truth table has columns at the left for those 3 literals and enough rows to account for all the possible combinations. Then as we move from left to right, we're going to build up our statement one operation at a time. Here is one possible way. It's not the only way, but it's a possible way to do that. We begin by declaring P, Q, and R. We're going to be done whenever we get the statement we want. Now, how can I build this? It's ultimately a conjunction. I need the left argument and the right argument of this conjunction, so those would have to exist to the left of this one. But if I had both of these columns done, I could conjoin them and be finished. How can I possibly get the negation of P or R? I have to have P or R. Can I construct P or R? Yes, because P and R already exist as columns. What about the conditional statement Q implies not P? I've already got the hypothesis Q, but I need the conclusion not P, so I have to declare that to the left sometime. Double checking, if we move from left to right, we've got 3 literals. And now, does everything involve one operation? Negation of P? Yes. Disjoin 2 columns that already exist. Negate a column that already exists. Make a conditional statement out of 2 columns Q, P that already exist. And then conjoin 2 columns that already exist. So this is now one operation at a time to get to the goal. What we now need to do is fill in rows. Well, let's start with our literals. There are 3 literals, each of which can be true or false. So I have 2 times 2 times 2 equals 8 possible rows, and that's how many are in here to begin with. What I need to do is make sure that I list out all the possibilities. Now, a lot of students at this point start haphazardly going, true, 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 maybe they're all true, or maybe it's true, false, false, or maybe they're all false, or maybe it's false, true, true, or maybe it's true, false, and false. And we're just sort of guessing, but observe that I've accidentally duplicated the same thing twice. If I do this, by the time I get to the end, I won't actually have 8 distinct rows. So I highly recommend you get your own sort of personal system to guarantee that you do in fact get all the possibilities. Here's what I like to do. Look at your last literal and alternate it. True, false, true, false, true, false, true, false. Then look at the next one and alternate it every other time. True, true, false, false. True, true, false, false. Then look at the next literal and alternate it half as often as that one. True, 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 false, 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 false. And now you can see that we actually have 8 rows and they're all different from one another. Okay. The first 4 rows are definitely distinct from the last 4 just based on P. These 2 and these 2 can be distinguished based on Q, as can these 2 and these 2. Then these 2 and these 2, sorry, this 1 and this 1 can be distinguished based on R, as can these, as can these, as can these. There's sort of a branching way that they all manage to be different from one another. But now that we have all of the rows we need and we filled in our literals, we can just go step by step. How do I complete the negation of P? I just look at P and I do the opposite. Where P is true, I'm putting a false. Where P is false, I'm putting true. By only needing to do one step at a time, I don't have to think very hard. How do I make the disjunction P or R? I just look at the columns P, R, and I ask, was either one of them true? If either this or this has a true in it, I can complete this with true. If both P and R are false, I'm going to put a false here. So P is true, R is true, true. P is true, R is false, the disjunction is still true. P is true, so it's true. P is true, so it's true. P is false, but R is true, so the disjunction is true. Ah, they're both false, so the disjunction is false. P is false, but R is true, so the disjunction is true. They're both false, the disjunction is false. Okay, what comes next is the negation of that. So all I have to do is look at this column and negate it, which is a very fast thing to do. I just look and I replace all my T's with F's and my F's with T's. Great, didn't take much thought. If I had tried somehow to jump just from P, R individually to this line here, I might make a mistake. Going one step at a time makes this very mechanical. Next up is the conditional statement, Q implies not P. So here's the column for its hypothesis. Here's the column for its conclusion. True hypothesis, false conclusion makes the conditional statement false. True hypothesis, false conclusion makes the conditional statement false. False hypothesis makes the statement vacuously true. That's also going to be the case in these last 2 rows here. Where Q is false, the hypothesis is false, the conditional statement is vacuously true. Now in these 2 rows, the hypothesis is true. The conclusion is also true in both of these rows. If the hypothesis and conclusion are both true, the conditional statement is true. Now finally, since I have this column and this column already built up, we can conjoin them by asking, do I see both of these being true? Yes here and yes here, otherwise no. So that allows me to complete this by saying, no, they weren't both true. 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 No, yes. No, yes. And ultimately what we have is we have built our way up one step at a time to complete a truth table for the statement we were interested in. Now, let's discuss something called tautologies and contradictions. What can happen is a very interesting property. Sometimes you can make a complicated compound statement with many different literals in it, but the end column that you get is always true or perhaps always false. In other words, regardless of whether the individual literals were true or false, the compound statement you construct is always true or perhaps always false. A tautology is a statement that is always true. A contradiction is a statement which is always false. These are very special statements that have some very interesting uses. If you can make a statement that is always true no matter what, it's called a tautology. If you can make a statement that is always false no matter what, it's called a contradiction. Let's take a look at an example. We're going to show that this statement, P implies Q, or P, is a tautology. Well, how do I show a statement as a tautology? We build its truth table. So it's got 2 literals, P and Q. So I start with that, and I need 4 rows, and here are the 4 distinct possibilities. One step at a time, I can form the conditional statement, and then I can do a disjunction out of this column and the first column, P. Well, if we go ahead and fill it in, true hypothesis, true conclusion, true hypothesis, false conclusion. False hypothesis, vacuously true. False hypothesis, vacuously true. Next, I want to do the disjunction, this column, with this one. Is either one of them true? Yes, they both are. Yes, P is true. Yes, the conditional statement is true. Yes, the conditional statement is true. And aha, this statement is always true no matter what. It is a tautology. Regardless of whether P and Q on their own are true or false, the compound statement P implies Q or P is always true. And remember, always true is a tautology. Okay, further discussion of tautologies and contradictions. If you have a statement that's a tautology, you can actually represent that with just a capital T, because no matter what, it's true. No matter how complicated it initially appears, it's always true, so just call it T for true. And a contradiction similarly can just be replaced with a big old F for false. The letters T and F in this sense as a tautology and contradiction can be considered as literals. So here, for example, is a valid statement. I have three literals, tautology, contradiction, and P. And I can then make the disjunction P or contradiction, and then I can make the conditional statement tautology implies P or contradiction. If you're making a truth table, however, since tautologies are always true and contradictions are always false, they do not cause a multiplication in the required number of rows. So how would I make a truth table for the statement we just discussed? In fact, it only has one literal that has any choice. Okay, there are three literals, P, T, and F, but P is either true or false, and tautologies are always true and contradictions are always false. So I don't need to have 8 rows here because I didn't have to do 2 times 2 times 2. There's only one possibility for a tautology and one possibility for a contradiction. So the total number of rows is 2 times 1 times 1 for a total result of 2 rows. A very easy mistake to spot for student submissions is a truth table in which they have a column for tautologies that include falsehoods or a column for contradictions that include truth. Okay, tautologies are always true. Contradictions are always false. And now we can complete the truth table. We disjoin. True or false is true. False or false is false. And now we can make the conditional statement. True implies true is true. True implies false is false. So this statement overall is neither a statement nor a contradiction, even though it did involve component literals, which are. Okay, just remember, using component literals, which are tautologies or contradictions, is fine, but it does not require you to multiply the number of rows in the table. Now we have a scary sounding math word, theorems. A theorem is just a tautology that can be constructed in a finite sequence of allowed operations, and that sequence of operations is called the proof or a proof of that theorem. This is a very strange sounding definition at first. Any statement we can make a truth table for, and if I can fill in the truth table, I can determine whether or not it is a tautology. So if I can make the truth table and I can determine whether or not it's a tautology, how could there possibly be a tautology that I can't show is a tautology? A theorem is a tautology which can be shown to be a tautology. Why is that not just the same thing? If it's not the same thing, it stands to reason there are tautologies that can't be shown to be tautologies. Well, in this stage of the course, tautologies can be shown to be tautologies. That won't always be the case. Okay, moving on to a notion of logical equivalence. Two statements P and Q are called logically equivalent if the following statement, P implies Q and Q implies P, is a tautology. In other words, is always true. Let's build up the truth table for that. So in general, if P and Q are just their component literals, notice this is not a tautology, it's also not a contradiction. But if P or Q happen to be compound statements, it might turn out that the final truth table you have for this conjunction of two conditional statements is ultimately a tautology. But in this truth table that we've built, when is this conjunction true? Only in the first row and in the last row. The first row is where P and Q are both true. The last row is where P and Q are both false. So if P and Q are the same as one another, this conjunction is true. If P and Q are different from one another, then the conjunction is false. So if this statement were always true, then the individual statements P and Q were either always both true or both false at the same time. Either way, they always do the same thing. Two statements are logically equivalent when they are always the same truth value as one another. Not necessarily always true, not necessarily always false, just always the same. We can abbreviate this conjunction of two different conditional statements with a biconditional arrow. So this arrow, P left right arrow Q, is said out loud as P if and only if Q. And it has the following truth table. It simply checks, did the two statements have the same truth value? If P and Q are both true or both false, the biconditional arrow says, yes, they were the same. If one is true and one is false, it says false, the two statements were different. So ultimately, logically equivalent means, based on what P and Q were as their own statements, this column would turn out to be a tautology. If that happens to be the case, there are a few notations for this. These mean very subtly different things that aren't going to be too important for us. P is logically equivalent to Q is this 3-line equal sign, or P if and only if Q.